this goes. So, the topic that we are going to analyze this week is so-called symmetric mappings. And we are going to find that we are going to, let's say, study symmetric mappings in terms of eigenvalues. And we are going to see what happens in the case of a symmetric mapping. Let us start with the very basic, and which is what's the definition of symmetric mapping. A symmetric mapping is a special endomorphism. And in a very, let's say, non-rigorous way, we may say that if f of x equal y is our mapping equal to ax, this mapping is symmetric if A is symmetric. Okay? So for the time being, it should be kind of clear. If you do not remember what a symmetric matrix is, which I hope is not the case, but just to be on the safe side, it means that if A is a matrix whose generic element is the element Aij, then for all I and j, it follows that Aij is equal to Aji. Do you understand this? Yes. And another equivalent way, which we might consider either definition or actually a proposition coming naturally out of this, a symmetric matrix is such that A and A transpose are the same matrix. Okay? They are the same matrices. So, this is something that we needed to know. And at first, I would like to tell you, why are we now discussing about symmetric mappings? They are quite important, or they are extremely important in mathematics, because many phenomena are symmetrics. One example of physical phenomenon that corresponds to a symmetric mapping is, for example, the gravitation. So, which means that, or any attractive phenomenon is inherently symmetric, because it means that the pairs of variables are interacting, the first one to the second one, as the second one to the first one. And you have many phenomena that are of this kind, and extremely many phenomena that allow us to represent the mapping by means of a symmetric matrix. Now, we will see what happens in this case, and what are the special properties of this mapping. At first, actually, I have to remind you one thing. Do you remember this notation? Inner product. So, inner product is a special function that makes correspond these two vectors, and the column A is a real number. Yeah? So it combines two vectors and it gives a real number. A special case of inner product is the so-called scalar product, that you know very well. And in that case, when it is a scalar product, so if x and y are elements of R n, this simply means that it is x transposed by y. Where the transpose is simply because I need to have the number of columns of the first vector that is equal to the number of rows of the second vector. Do you understand this? Yes. So, now I would like to introduce to you, in a subtle way, another concept, and it is, if I consider a certain matrix A, that it doesn't matter whether or not it is symmetric, and I multiply the matrix A by a vector x, what do I get as an output? A vector, don't I? Therefore, I might think about performing this operation. Okay? And up to this point, it seems kind of an easy thing. I am simply getting a vector, which I'm going to call AX, and I'm performing the scalar product of this vector by this vector. Nothing strange. But if we look at the things from, let's say, a deeper or a higher perspective, what am I doing is somehow to introduce a scalar product by means of a matrix. So if my inputs are AX and Y, then there is nothing to say. It's what we already know. But if my inputs are X and Y, then what I'm doing is to introduce a scalar product by means of a matrix. And the scalar product by means of a matrix is clearly an inner product. So this would be an example how a scalar product is a special case of inner product, while an inner product is a generalization of the concept of scalar product. Fine? So this should give you more context also with respect to what you studied in calculus. Okay? And another important thing, so I'm really just scratching the surface, as you might say. And another odd thing that you might see is that AX is f of x. So now, to say this can also be seen as a multiplication of a function by a vector. What does that mean? Now things start being a little bit more complicated. But let us see the next theorem, and let us see what happens if A, bless you, if A is symmetric. And let us switch the microphone on to make sure that I'm clear enough. Theorem. Let us consider two vectors, x and y, that belong to Rn. And let us consider a certain matrix belonging to Rn, and A is symmetric. It follows that Ax, comma y, so this inner product, or if, let's say at the moment we say that we are working with real numbers, so this is like a scalar product, is equal to x, a, y. So there is this strange symmetry with symmetric mappings. Now, before we prove it, let's go back for a second to this. So it means that if I can define a special scalar product by means of a matrix, I can move the matrix from one side to another. And what does not look probably too obvious is that if A is symmetric, then this thing is equal to this thing. Which is something that I do not expect you to understand in depth. But what I would like is that you feel confused. Meaning in a good way, like that you feel intrigued about the fact that there is something underneath. And even if you do not understand this in depth, it doesn't matter. You understand at least this formula up to now, more or less. You understand that this is a multiplication of a matrix by a vector, and this is a multiplication by a matrix by a vector. Of a matrix by a vector. And you can move, somehow you can slide this matrix from this side to this side. Let us see why. The proof is not difficult at all, simply requires that you understand what is the definition of scalar product. And the definition of scalar product is written over there. So x, y is x transpose scalar y. Yeah? So, which means that ax, y is ax transpose scalar y. Okay? But what happens if I have A by B transposed? Do you remember? No. A B transposed is B transposed, A transposed. Okay? And this is equal, it's on chapter 2. Actually I've even included a proof of that. I don't know if maybe in the new version. Is X transposed, A transposed, Y. Okay? So the first thing that I do is that I consider that the scalar product is associative. And then I consider that if A is symmetric, A is equal to A transpose. Therefore, this is X transpose, A, Y. Which means what? It means the inner product of X, A, Y. Proof. Okay, let us see what this means in practice. This is nothing. This is easy to. So let us analyze the situation. What do we need? We need two vectors and we need a symmetric matrix. Let us keep the things easy, just not to challenge ourselves too much with arithmetics. And so x is 1, 0. Y is 2, 1. A is 1, 5, 5, 2. Okay? This is symmetric. Now, first exercise is to calculate A by X. A by X is 1, and here we have 5. Am I right? 1 by 1 plus 0 by 5, 5 by 1 plus 0 by 2. And now that we have this, we calculate AX scalar Y, which means that we have to calculate that one by that one, which means 2 plus 5, 7. Okay? Now we do the other things around. We calculate AY. And to calculate AY, we need 2 plus 5, 7. And 5 by 2, 12. And now we need to calculate this one by X. And by X, which is, so we need to calculate 7, 12 transposed, which is going to be like 7, okay? Well, it doesn't matter now. 1, 0. So we get what? We get 7. And that's the same. Okay? This is going to be really relevant to us. Okay, so what I'm telling you is, I've shown you this property. This property is really important because I'm going to use it in all the next proofs, in all the proofs of the day, for today and tomorrow. To understand really what that means is going to take way more than 2 years of maths. It's going to take way more time. But you keep in mind that thing exists. Okay, now we complicate our life just a little bit. And we complicate our life by saying, okay, well, what happens if x is an element of the complex number to the power of n? And y as well. Sorry, this is an element. X and y are elements of x and y to the power of n. And A is, let's say for the time being, it's an element of n and, let's do it like this, C and n. And, but A is also symmetric. What happens? So at least I feel that I need to let you know. And I need to let you know also because of what I need to tell you later. Do you remember what is an Hermitian product? An Hermitian product was, I will tell you now.
It's a transposed conjugate.
Yeah, so these are complex vectors. So if I want to calculate the Hermitian product, I need to calculate the conjugate, I need to transpose it, and I need to calculate the scalar product of these values. Okay? Well, you know how to calculate the conjugate and how to calculate the transpose. And then, and you know how to perform the product and sum of complex numbers. So you can put everything together and you get an Hermitian product. Now, what I'm going to tell you is that if we are working with complex numbers, what we have is that it's nothing too interesting, but let us see, is that this is equal to, of course, x, comma, still we get an A transposed, and then we get to y. Sorry, a conjugate, not transposed, yes, sorry. So what I am telling you is that the perfect symmetry. Yes, sorry.
So it should be also saying A conjugate X, or is it AX? It's like there you said that AX, Y, and then X. A.
X is A. X.
Yes, yeah, but what about A in the first one? Is it A conjugate? Or
No, this is A.
Thank you.
So essentially, what I'm telling you is that if A is made up of real numbers, it simply slides here with no issues. If it is with complex numbers, it slides, but then there is this, let me say, this conjugation issue that you have to keep in mind. Okay, now let us prove it. Well, the proof is simply that this is an Hermitian product, therefore, proof. This is an Hermitian product, therefore, we have parenthesis, A, X, parenthesis, conjugate and transposed. Scalar product, Y. One thing that I have not told you probably clear enough last year, but now we're going to include the proof in whatever chapter is, maybe chapter 5 of the complex numbers, is that the conjugate of a product of complex numbers is equal to the product of the conjugate. Okay? But you can easily prove it yourself working with Z, A plus B, and A minus A plus JB, A minus JB. So this is going to be equal to A conjugate, X conjugate, all transposed, scalar product, Y. Now, still, we have that this is going to be X conjugate and transposed, A conjugate and transposed, Y. Parenthesis, because of the associativity, and still, since A is symmetric, then this is X conjugate and transposed, comma, A conjugate, Y, no, not comma, Y, dot, sorry. It's like a product, so, and now I can rewrite this as X, comma, A transposed, Y. Okay? Now, yet again, I am gonna need this, actually for the next proof. I might give you a numerical example if you want it. It can be good, probably. Sorry. Or shall I make it up? Yeah, let's make it up. I mean, we made it 2 by 2. So, we pick up X, be nice with me, 1, 0. Y is going to be 2J. And then we have A, and let us make it easy. 1, 2, 2J. Fine? These are complex numbers. Easy ones, but it's fair enough. AX is equal to 1 and sorry, and 2. Am I right? I hope so. Then 1, 2, AX, Y is going to be equal to 2 plus 2J. I need to get the same number when I do the things the other way around. Or actually, I should get AX and Y, that's fine. Now, I have to calculate A conjugate, which means 1, 2, 2 minus J. And now I have to calculate A conjugate by Y, which means 1, 2 by Y is 2 plus 2J, and here we have 2 plus 2J, and here we have this one by that one, which means 4. That's the difficult one. Plus minus j. J by j is minus 1. Since there is a minus here, it should be a plus 1, if I'm right. Is it correct? I hope so. But anyway, it doesn't matter because it's going to be multiplied by 0. But anyway, it should be this. 2 plus 2j. Fine. Now, we calculate the scalar product of this one by this one. So we have, well, it is essentially x conjugate, which stays x, multiplied by a dot j, and this is going to be equal to 2 plus 2j, which is equal. Well, I should put the things this way, but it doesn't matter because the scalar product. No. So this is fine, and this is fine, and these are the same thing. Okay. I hope that this somehow clarifies. But yet again, do not worry too much. I am going through this proof because of the next proof. That is really what is interesting to us, and I have to build up. I mean, the reality is that I need to tell you something, and it is how to calculate the eigenvalues in the case of a symmetric mapping. And I realized that in order to give you a proper justification, I needed to dig in some slightly more difficult maths, which I tried to simplify as much as I could, and at least to give you an idea. So now that we know that this is true, I can make the next proof. And the next proof is going to be way more interesting. Here, F is an endomorphism. And let's say where the matrix A associated to the endomorphism is belonging to R and N. And A is symmetric. So it's a symmetric mapping made up of real numbers. It follows that the eigenvalues of F of the mapping are all real numbers. Okay? So, this theorem tells you that if you look at the symmetric mapping, the characteristic polynomial is necessarily having all real roots. All the eigenvalues are real. Okay? So you don't get complex numbers out of it. Why? Let us say how this works. Proof. It's not too difficult, but it requires a bit of attention. I mean, this is the end of the course, so it's the last sprint. By contradiction, let us assume that lambda, eigenvalue of this mapping, is a complex number. And it is such that x is the corresponding eigenvector. Okay? In this situation, if this is the case, we might consider lambda, since lambda is a complex number, we might consider the lambda dot conjugate of that complex number, because it's a complex number. So it has got some imaginary part, then we think about the conjugate. And we multiply this by the inner product, by the Hermitian product of x, comma, x itself. Okay. So this is the Hermitian product, and this is going to be equal to what? Hermitian product of lambda x, comma x. Am I right? Why? Because the Hermitian product is the transpose of the conjugate, therefore if I put the conjugate inside here, the dot disappears, if that makes sense. And then if I wanted to calculate this, I needed to do something like lambda x dot transpose, which is equal to lambda dot x dot all transposed by x. That's what that means. But this is an eigenvector Therefore, this is equal to AX. X. But, well, we know, especially when since A is made up of all real numbers, we know that I can slide the matrix to this side. Therefore, this is X, A, X, isn't it? And I can do that because A is made up of real number. Therefore, it's equal to its conjugate. Okay? So, I can slide this over here, and then what happens? It happens that this is equal to X, comma, lambda X, isn't it? Which is equal to X, comma, X, lambda. So I'm writing here, effectively, so I can, for example, cancel this scalar product over here because it's just it's a product. These are like real numbers, and then I end up saying that the conjugate of lambda is equal to lambda. What does this mean? If I have a number, a complex number, that is such that it is equal to its conjugate, what can I conclude? Exactly, which means that it is real. So, and if you don't understand this fact, I can say it in this other way. Let's say that lambda is a complex number of the type A plus JB. Therefore, lambda dot is A minus JB. If I tell you that these two things are the same, what do I conclude? I have to conclude that this is 0, not I. Therefore, A, then we have got only A, which means that lambda is a real number. Okay? So, first caveat here. I have made an hypothesis. And it is this one. This means that this theorem is valid as long as we are working with real numbers in terms of matrix. If here we put a complex matrix, then this is no longer working. Okay? So out of a complex matrix, even if it is symmetric, we might have some complex eigenvalues. While in the case of real numbers, we are totally sure that our eigenvalues are going to be real. Shall we look at one example? Let us see what time is it. No, I will try to give you an example later. I want to show you one more theorem. Okay, then I cancel this. So we know up to now that if A is composed of real numbers and it is symmetric, then all its eigenvalues are real. Now I'm going to tell you another thing, that if F is an endomorphism, which goes from E to E, and A is a matrix composed of real numbers, and A is symmetric, then there is another important property. That if I take, let's say, two eigenvalues, let's say like this, for all I and j, let me write in actual math, lambda A and lambda j, with lambda A different to lambda j eigenvalues, follows that the xi element of v lambda I and xj element of v lambda j. Do you understand this? Do you? You don't remember? Okay. This is the eigenvector, and this is the eigenspace. So, and then it follows that xi is orthogonal to xj. So I try to repeat this in a more friendly way, and it is if I consider two distinct eigenvalues and the two corresponding eigenvectors, I'm sure that those two eigenvectors are orthogonal. Okay? So I'll try to prove this. and then I'll give you an example to show you these two properties at the same time. First, we might consider the inner product of, in this case, it's enough that it is a scalar product because we are working with real numbers, and we already know that it doesn't matter because if this is real, these are definitely real numbers. So we might consider this scalar product. And we know that if the scalar product is equal to 0, then it means that the two eigenvectors are orthogonal. We multiply this by lambda I. If I multiply this by lambda I, this is going to be equal to the inner product of lambda I xi, comma, xj. And this is going to be equal to a xi, xj. You with me? But I can slide the matrix over here, can't I? Therefore, this is xi, comma, a xj. Which means xi, comma, lambda j xj. Which means equal to xi, xj, lambda j. Okay? What am I concluding? I'm concluding that this is equal to this, and I know that lambda I and lambda j are different. So if they are different, it means that they cannot be 0, at least not both of them. And the only way how this equation can be verified is if xi and xj is equal to 0, which means that xi is orthogonal to xj, which is How do you feel about this? Is it okay? Is it difficult? Well, it requires a little bit of thinking. I'm trying to make it easy, really. And now we do a simple example, and I show you empirically how these two things are true. And I have prepared one with easy numbers so that we don't have to calculate square roots or anything. And it is this one. F of x and y, 5x plus y, x plus 5y. So, f of x and y is 5x plus y, x plus 5y. Okay? So, this is, of course, at first, it is an endomorphism, which goes from R2 to R2. Right? And the matrix A associated to this endomorphism is 5, 1, 1, 5. Okay? Let us calculate eigenvalues and eigenvector of this endomorphism. At first, we have to calculate the determinant of 5 minus lambda, 1, 1, 5 minus lambda, which should lead to lambda squared minus 10 lambda.
Minus.
No?
Oh, yeah, maybe. Sorry.
Plus 24. That's what we should get. And out of this, we can calculate the roots that are lambda. It's equal to 4 and 6. So first consideration, these two eigenvalues are real numbers. Let us now the real calculation that is easy for the eigenvectors. Okay? So to calculate the eigenvectors, if you don't remember, what I have to do is effectively to solve this system of linear equation. X plus 5 minus lambda y equals 0. And I need to insert it at first 4, and then I have to insert 6. When I put 4, I have x plus y equals 0. And here I have x plus y equals 0. Quite easily, I can say that x is equal to minus y. And if x is equal to alpha, y is going to be equal to minus alpha. Essentially, what I'm saying is that the eigenvector is one eigenvector is 1 minus 1. Okay? What happens if I plug 6 in that equation? If I plug 6 in that equation, I get minus x plus y equals 0, and x minus y equals 0, which simply tells me that x is equal to y, which is equal to alpha, which means that I have 1, 1. Now, I can pretty easily see that the scalar product of these two vectors is 0. What does that mean? It means that these two vectors are orthogonal, which means that you should always think about the geometric meaning of what we are talking about, or the geometric meaning of the algebra. So you might think that we are doing an exercise inside R2, which is like a plane, and we have found, so let's say this is our plane, then we have 1, 1, that is the second vector here, and we have 1, 1, 2, 2, and so on. So we have that this would be an eigenspace, and the other eigenspace is 1 minus 1, is the one like this. And what the second theorem, the last theorem I've proved today, is that this angle is 90 degrees. Okay? And well, and then actually to see okay, let's say the eigenvalue is a real number. To see that the eigenvalue is a real number on this graph is something which is much more complicated, and I'm not demanding you to realize that, but there is a way. Okay? So I think that for today is enough. Are you okay with everything? Are you fine to some extent? Okay, thank you very much. We continue tomorrow.